lectures or the like. Feel free to raise a virtual hand here if you would like to ask. And if you haven't already, please feel free to chime in via the chat as to where you are in the world. Let's see. Any virtual hands so far? See, we have someone from Nepal, Ecuador, Mexico, India, Czechia, England, Tokyo, Bangladesh, Canada, 2 Bangladesh, Spain. OK, now they're really coming in. OK, Russia, India, UK, Newcastle, Australia, Chile, Algeria. OK, excellent. OK, Gung, if I'm pronouncing it right. Question from you first.
Yeah, hello, David.
Hello.
I just have a little bit of question about the previous lecture, a little bit about antivirus.
OK.
Can or how does AI helps antivirus in recognizing viruses in like the case of zero-day exploit, for example? Do they like enhance the, was it pattern recognition or something regarding the antivirus?
Theoretically, so AI, or artificial intelligence, is pretty good at recognizing patterns that humans might not otherwise notice themselves. And so when it comes to zero-day attacks, which recall are attacks by malware that was just invented or just released today, and therefore your antivirus software might not know about it yet, through AI and pattern recognition more generally, the hope is that you could detect that, wait a minute, like Gung's computer has never sent 1,000 emails all at once. He's probably infected. And so AI could sort of notice that kind of pattern without someone having to have written code to detect that specific pattern and then perhaps shut down your computer or stop your email functionality so that it can no longer proceed. So I would associate AI really with pattern recognition, but without needing to have, if I see this pattern, then do this. Else, if I see this pattern, then do this, and so forth. It's more dynamic than that. So a good question, and I'm sure this will continue to evolve over time. If you're just joining us, still just doing a couple of questions before we begin. Raymond?
Hi, that was very fast. So my question is about our 4 classes, which is around, I'm not sure when, and so that will be my question, like when will be our 4 classes about CS50X, and the second question is about how do we use AI for debugging or troubleshoot our codes, which will be included in our 4 classes.
Sure. If I understood you to ask about fall classes for CS50X, those won't be until September, October, and November. So we'll email and announce that in a couple months' time, most likely, if not sooner. And as it relates to AI and programming, so this is a world that's changing quickly. There are tools in the real world already called GitHub Copilot, Amazon Code Whisperer, and a bunch of others as well that essentially have analyzed thousands, millions of lines of code that people like you and me have already written in the past and use that, similar to our discussion of zero-day attacks a moment ago, to recognize patterns. And so if you enable features like GitHub Copilot in VS Code, you can have these tools essentially autocomplete your code more powerfully than was traditionally possible with non-AI-based autocomplete. Usually non-AI-based autocomplete just looks for, literally tries to help you finish the name of a function or the name of a variable that you're trying to type. But AI tries to finish the entire block of code or the entire function of code or the entire file of code that you're actually trying to write. And it uses patterns that it's seen before to try to infer from those and also from documentation that it's analyzed what it is you might want to do. So within CS50.dev, which is CS50's own programming environment that is used in CS50X, our intro to computer science, we're starting to add those features this summer. So more on that to come too. And how about one more question before we begin for real here? Tom?
Hi, David. My question is that how can a proxy server assist in protecting against web application vulnerabilities, such as cross-site scripting attacks?
Well, that is a perfect segue to today, because we're going to talk about literally that topic. So allow me to wait just a little bit till we get to that point in the class. All right, give us just a moment to get ready, and then we will begin. Oh, and we should do the souvenir photo. Is Mike still on? OK, before we begin, why don't we take this here souvenir? Oh, not that. Where'd it go? There we go. This here souvenir photo. So if you'd like to opt into this, go ahead and turn on your camera. If you'd like to opt out of this photo, turn off your camera. And we'll give folks a few seconds in case your camera takes a moment to enable. But I'm going to go here and put on my best smile and wave. And if you'd like to do the same, we will then post this on the course's website afterward. And Rungshin, could we invite everyone to say hello verbally too, if you can click two things at once?
Uh-oh.
Hello.
Yes.
Hello. Hello. Hello.
Yes.
Hello. OK, I think we're good. Let us remute everyone. OK. All right, this is CS50's Introduction to Cybersecurity. My name is David Malan, and this week let's focus on securing software, whether it's software you use as a user or software that you write as a programmer. Recall, for instance, one of our topics from earlier in the class, phishing, this attempt by adversaries to try to phish or obtain information from you. Let's consider today from a software perspective how someone might go about implementing this particular attack, and equivalently how you might go about preventing or detecting or keeping yourself immune from this very attack. Actually, can we start this over? Sorry. OK. Sorry, y'all. Mic still up? OK. All right, this is CS50's Introduction to Cybersecurity. My name is David Malan, and this week let's focus on securing software, whether it's the software you use or whether it's the software you write as a programmer. Consider, for instance, one of our topics from earlier in the class, namely phishing, this attempt by an adversary to phish or obtain information from you. Let's consider today how you might go about implementing this kind of attack, and equivalently how you as the user might go about noticing an attack like this. Well, here again is a language called HTML, Hypertext Markup Language, and it's the language in which web pages are written. This is maybe the simplest example that we could put together that represents the kind of text that a web server would send to a web browser when it wants to display information on your screen, be it the day's news, your email inbox, or anything else that is web-based. ... is where I've put placeholders just to represent where some additional code might actually go, like the content of this actual web page. Well, for instance, suppose that we consider in the abstract just a simple example of these so-called tags. And in fact, recall that everything that you just saw sort of had these open brackets, but also the same words again and again. For instance, if we wanted to have a paragraph in this language called HTML, we would have this thing here called a tag, or an open tag, or a start tag, and then this thing here at the end, a end tag or a close tag. And those are meant typically to be symmetric. This one sort of begins a thought for the browser. Hey, browser, here comes a paragraph. And this one here with the / inside of those angled brackets means, hey, browser, that's it for the paragraph. So anytime you see HTML in a file, it's really telling the browser what to start doing and what to stop doing. So here is how a browser, therefore, might know that it needs to display a paragraph of text, maybe separated by some white space by other paragraphs of text. Here, for instance, is how a browser might know that there's some code inside of the web page, typically written in a language called JavaScript. So this script tag opening here and this close script tag here would be, hey, browser, here's some code to execute, ... and hey, browser, that's it for the code to execute. So how might there actually be a threat or an opportunity here for an adversary to phish information from you? Well, here, for instance, is how you might, in this language called HTML, create a link, otherwise known as a hyperlink, in a web page. And it, too, uses an open tag and a close tag. This A tag represents an anchor, like anchor some hyperlink, some link in the web page right here. And this tag here means, OK, that's it for the link. And if we want to link, for instance, to Harvard's website, in between that open tag and close tag, would you actually put the text of what the link is meant to be? So if you want the user to see a link on the page that says Harvard, you would put literally Harvard between this open tag and close tag. But that's not actually enough to link to some other page. You have to tell the browser what URL or what file you want clicking on Harvard to actually lead the user to. So for that, we need to introduce one other concept in this language called HTML, namely an attribute. So href stands for hyperreference, and it's a fancy way of saying this is what I want the browser to link the user to when they click on that word Harvard. Now, at the moment, I've just done a ... but that would, for instance, be the URL of Harvard's own website. So consider this very specific example now, whereby we still have our anchor tag opening here. We still have our anchor tag closing here. We now have, though, an href attribute that's telling the browser that when the word Harvard is clicked, I want the user to end up at https://harvard.edu. So that all seems fine and good, and this is the way the web is supposed to work, and this is what links in your own web pages will look like if you poke around underneath the hood. So where's the actual danger? Well, hopefully there is none, and hopefully when you open this kind of HTML in the context of a larger file with even more tags than just this anchor tag, you'd see a browser window that looks a little something like this. You'd see a link, typically underlined, though not necessarily, to Harvard, and then and only then, if you hover over that link, can you see where you will go, even if you don't actually click the link. So suffice it to say, if you just click the link, you're going to end up on Harvard's own website. But if you a little more cautiously, with a bit more paranoia, a bit more consciousness now of cybersecurity, hover over that link and focus on your browser's bottom left-hand corner typically, at least on a laptop or desktop, you'll actually see the URL to which you will actually be whisked away when you click on that link. So this actually looks OK. The word here is Harvard. The URL it's going to link me to is https://harvard.edu. So I think all is well in the world. And indeed, you can do this on most any web page on your laptop and desktop if you want to proactively, preemptively see where it is you're going to go before you actually click on that link. So where's the danger? Well, let's get a little more specific and a little more malicious, if I may. So here we have the exact same HTML as before, but let's go ahead now and not just say Harvard inside of this open tag and close tag. Suppose that for whatever reason, I want the user to see a little more obviously the URL to which they are going to be linked. So I might change Harvard, capital H, to harvard.edu. So the actual domain name that I want the user to be led to. Here is now what the user would see. So it's a little more obvious that it's harvard.edu and not some other Harvard website. And indeed, if we hover over that, we'll see that it still is going to the same URL. All right, so that seems fine and not all that enlightening. Let's go one step further. Suppose that you really want the user to see a URL in the body of the web page. So now I'm actually going to put in between the open tag and the close tag https://harvard.edu. Now notice this looks a little redundant, and it is in some sense because I literally have the URL in two different places, but that's because those two values serve different purposes. The one in between the open tag and close tag is what the human sees. The one inside of the quote marks, the so-called value of the href attribute, is where the user will actually end up. So if you want them to be equivalent, you have to type the exact same thing twice in this case. So now, of course, if I go back to the web page, the human is now going to see literally this URL. And if they hover before clicking, they'll see confirmation as much. So where are we going with this? Well, here's among the lessons of the course is to think about now how can you take a perfectly reasonable technical solution to a problem, creating a link and a page in this case, and how might an adversary abuse it? How might you as the end user be vulnerable in this case to a so-called phishing attack? Well, there's nothing stopping me from putting anything I want in either this value or in this name of the link. So you know what? Why don't I be a little malicious here? And why don't I tell the user that they're going to harvard.edu, but they're actually going to yale.edu instead, another school down the road. So what does the human see now? Well, if we go back to the browser, they still see what appears to be https://harvard.edu. But if they hover over it, and only if they hover over it, will they see this little clue that, you're actually going to be whisked away to yale.edu. And if they click on the link, they'll actually find themselves at the actual yale.edu website. So what's the big deal? Well, this might just be a silly prank, in which case it's probably inconsequential. And if you do link from one website to a completely different one, it's not necessarily a phishing attack. It might be confusing because the user thinks they're going to Harvard, but they find themselves at Yale. But there's not necessarily any danger in that mislead. But what if the adversary in this case doesn't link to a very common, popular website like yale.edu, but maybe a website like harvard.edu where just one of the characters is slightly misspelled, as we've discussed in the past? Just that you and I, unless we really, really look carefully, we might not even notice that we're not at the real harvard.edu. And what if further, the adversary went through the trouble of copying all of the HTML that implements Harvard's website and pastes it into their own fake version of Harvard's website that lives at, again, a URL that is almost the same? Here is now where there's a phishing opportunity, because if you think you're going to harvard.edu and you click the link and it looks like you're at harvard.edu and you don't notice a subtlety like, wait a minute, that's not quite the right URL, you might now be inclined to and comfortable with maybe logging in to the fake harvard.edu website with your username and your password, and voila, now the adversary has that information from you. And it doesn't have to be Harvard. It doesn't have to be Yale. It might be your bank. It might be PayPal.com or something where you could actually lose money, or some other asset you care about. And so that's really the essence of the implementation details of a phishing attack, at least in the context of web pages and or emails. It all boils down to these primitives of HTML being the language in which web pages are written, and adversaries, by knowing HTML, also now logically can misuse HTML by understanding how these basics work. So let me pause here and see if there's any questions about phishing or HTML or this convergence of the two when it comes to this form of social engineering, as we called it before. Utkarsh?
Hi, David. Yeah, so my question is that nowadays we see a lot of antivirus softwares that allow us to use a browser sandbox, as they call it. So what does this sandbox protect us from? Is it just from viruses, or is it also for phishing links and stuff?
Can you elaborate? What kind of sandbox are you referring to?
Like, say I install Avast as an antivirus, and it has a feature, a browser sandbox, which is supposed to protect me from viruses and malwares before opening a site. So it tells me to open any fishy links in the browser sandbox instead of my exact browser. So what does it protect me from? Exactly.
OK, a good question. And I can only hypothesize based on the description you've given me. But typically, a sandbox refers to, much like a child might play in a sandbox outside, and there's an edge to it to keep them sort of in the sandbox. The same principle applies in the digital world, where a sandbox is a virtual concept that sort of puts firewalling-like boundaries around what it is you're trying to do. And in this case, if this software you're describing provides you with a browser sandbox, what it's probably doing is anytime you click on a link, it is first checking, is that link known to be a potential threat? Google, for instance, does this with their Chrome browser. When they hear about fake harvard.edu websites, they might add that fake website to a special list that they have, so that if you or I try to visit that the next day, we actually will be prevented, or at least discouraged, from clicking on the same. Alternatively, what the software could be doing is not even waiting until you click on the links, but anytime you visit a web page that has HTML, like this hyperlink here, it could be looking at that HTML, looking for dangerous URLs, and maybe changing them or just preventing you from clicking them all together. How about one other question here on phishing or HTML? Yeah, Alex?
Yes. Hi. We said that the domain registers try to prohibit registering fake websites, right? Mm-hmm. So would it be possible to write my IP, or, well, not my, somebody, IP or some other means to get to their website and not the URL? So they, because if they registered the URL, I can see who it is, who registered it. Mm-hmm. Other ways to sorry, to go to skip that.
Short answer, yes. If you have access to dedicated IP addresses, which are these unique identifiers you can use for servers on the internet, you can absolutely have a URL that is like http:// and then the IP address. Now, typically, it would be HTTP and not HTTPS when using an IP address, in which case that might be a clue to the user that, wait a minute, this is making me nervous, that this isn't legitimate. But honestly, I think we can all think of people in our lives who wouldn't have the instincts to notice, wait a minute, what is this weird numeric address in my browser bar, and stop what they're doing. That's indeed among the goals of the class like this, is to give you those instincts and that training beginning to be a little suspicious when you see something like a raw IP address in the browser. Technically, there's nothing wrong with it, but it's a little bit of a weird branding or marketing decision for a website. And I think a corollary of this then, logically, is that if you are running a website of your own, or if you're running a business with a website of your own, you should really avoid using many different URL formats or many different domains or having any sort of curiosities or weirdnesses in your domain names, because you're really just teaching users implicitly that your URL format might change from time to time. And certainly you never want to use just an IP address because you're going to train people to expect that. And so standardizing on one or very few domain names or subdomains is generally best for that. And let's go ahead and resume in just a moment. And Carter or Ian or Andrew, can we send off one more note? Because I'm definitely still feeling it down here today. OK, if we can crank it more. All right. So what are some other attacks that we should be mindful of when it comes to our own software? Well, a class of attacks or category of attacks are generally known as code injection, which is an opportunity for an adversary to somehow inject code into your software and often trick your software into executing that code, even if you yourself didn't write it. Well, let's consider one example of this. A common attack on the web in particular, too, is what's known as cross-site scripting, or XSS for short. Cross-site scripting refers to this potential opportunity for an adversary to trick one website into executing code that they, again, themselves did not write. So what form might this actually take? Well, suppose that you yourself visit google.com, and suppose that Google isn't aware of this particular attack. They certainly are nowadays, but suppose that they weren't yet aware that this attack exists. And so when someone like you or I goes to google.com and searches for something like cats, suppose they do the following. They show you a whole page of search results, and I won't bother showing the actual results, but as of today, there were 6,420,000,000 cats on the internet that Google knows about. And they would show up, of course, down here. Now, notice a few characteristics about google.com as it typically behaves. Well, one, you still see a text box containing what it is you searched for so that you can change it or at least see what it is. And notice, too, that in smaller text here, in this particular version of Google, it tells you not only how many results there are, but specifically how many cats there are. So that is to say, if Google is using your own input, not only to remind you of what you searched for in the search box, but also in the body of the web page, that very simple idea is vulnerable to an attack. Why? Because who wrote the word cats, C-A-T-S? Well, it wasn't Google per se, it was me. Now, fortunately, cats in and of itself is not dangerous, but suppose I knew a little something about HTML and browsers and how the internet works, and suppose that I now, an adversary, did something like this. And knowing that Google is probably inside of their web page rendering HTML that looks like this, a paragraph of text per the open paragraph and close paragraph tag, and an English sentence like this, about 6,420,000,000 cats, if I know they're putting my input, cats, into HTML that looks like this, let me see if I can try to trick Google into outputting something that they might not have anticipated. So instead of cats, let me type something of a little weird that looks like this. Now, what are we looking at? We're looking at now an HTML tag, the script tag, both opened and closed here, and a little bit of code in a language called JavaScript. Now, thankfully, this in and of itself is not actually a compelling attack. It's literally just going to display attack, quote unquote, on the screen. So it's just meant to be representative, I claim, of how I could potentially trick a website like Google into executing code that I wrote, not that they wrote. So what do I mean by that? Notice that I've got this open script tag here and the closed script tag here, which means everything in between there is script, that is JavaScript, this particular language. Well, it turns out this particular language, in the context of browsers, comes with a function, a feature known as alert. And if you want to alert the user with some message, you literally write the word alert, and then an open parenthesis and a closed parenthesis on the left and right. And then inside of single quotes or double quotes, you put whatever word or words that you want to alert the user to. So this is often used for displaying messages to the user. Not actual attacks, but useful messages. And there's more elegant ways to do this as well. But this is the simplest representation of an attack that I could propose here. Now, I haven't yet hit enter on this page because indeed we still see that we're on the page relating to cats as my search result. But as soon as I hit enter after searching for this string of JavaScript code, or really HTML inside of which is JavaScript code, what might happen? Well, this could potentially happen. Now, again, this is not a bad thing in this specific case. It's just throwing up an alert to the user. And in this sense, too, I'm really only attacking myself. Because if I'm the adversary, and this is my browser, and I've just tricked Google into executing some JavaScript code such that a pop-up appears saying attack, well, I'm just like hacking myself. So this is inconsequential. But again, it's representative of how we could potentially trick a website into executing code that they did not intend. Now, why is this displaying? But notice no more cats and no input here that I typed myself. Last time when I searched for cats, I saw the word cats here. But now I'm seeing nothing at all. Now, why is that? Well, underneath the hood previously, I claimed that Google was probably rendering HTML like this. A paragraph of text, open tag, close tag, and then the sentence about 6,420,000,000 cats. So HTML, and they were just plugging in whatever I, the human, typed in. Well, this time I conjecture that if I typed in what looks like and is HTML with a bit of scary JavaScript code in between, what Google is probably going to try to output in the body of the web page they send to my browser is this: an open paragraph tag and a closed paragraph tag. Still the beginning of a sentence, assuming that there are this many attacks in the world, 6,420,000,000. But notice this. Because I, the user, literally typed in the script tag and the close script tag, and then that JavaScript code in between, the browser doesn't know that that came from me and not Google. So the browser is just going to read this as, hey, browser, start a paragraph about 6,420,000,000. Hey, browser, here comes a script. That is a program that you should execute. What do I execute? Alert, quote unquote, attack. Hey, browser, that's it for the script. Hey, browser, that's it for the paragraph. So if Google is just blindly copying and pasting what I, the human, am typing in, I might trick Google into rendering HTML that Google did not intend. And the side effect in this case is that I see this alert, but really that's indicative of a potential exploit in Google's website if they were not detecting this on their own. So this is the code that's dangerous. And what then is the fundamental problem? They are just literally outputting what I, the adversary, typed into their page. So how do we go about mitigating something like this to avoid this kind of attack? Well, let's first propose that what we want the effect to be is something a little more like this. Assuming, again, that there are 6,420,000,000 attacks in the world, what I want to see is literally that English sentence here. I don't want any sort of pop-up. So this, I would propose, is the correct behavior, assuming we see more search results down below. I have searched for this. Google is telling me or reminding me what I searched for, but there's no pop-ups in this case. So somehow or other, based on this screenshot alone, there must be a way of ensuring on Google's end that even if the human types in HTML with perhaps some JavaScript code in the middle, that they don't actually treat it as HTML and JavaScript code in the middle. They just display it literally, character by character, whatever I, the user, typed in. So what is this representative of? This is what's known as a reflected attack, whereby, at least in this model, I have created a scenario where the attack is sort of reflected back on me, the user, who clicked on or initiated that interaction with the browser. So what do I mean specifically? Well, suppose that an adversary is trying to now get a user to be tricked into suffering this kind of reflected attack that happens to them. Well, suppose that the adversary doesn't just tell the user to type in the JavaScript code, but suppose an adversary constructs a very clever link using HTML, and maybe in an email, maybe on their own web page, tricks a user, not themselves, into clicking that link. Can we maybe achieve the same behavior as we saw on google.com a moment ago? Well, we actually can as follows. Here now is some HTML representing the beginning of a link. This is our anchor tag starting. This is our anchor tag ending. And somewhere in these quotes, ... is the URL that we want to lead the user to. All right, well, what could that be? Well, if I want the user to actually be able to search for cats, it turns out that I can specify a href value of https://www.google.com/search question mark q equals cats, where q represents query, cats is what the human typed in, and what the human will see in this link, if this link is included in an email or the adversary's own website, the human will see cats, and the link will take them to a search page containing those cats. So why is this relevant here? Well, suppose that if instead of cats, we typed in something, let me fix that. Let me pretend like I had a slide here. Let me just fix this real fast. Sorry, y'all. OK, let me just rewind slightly on our team. OK. So what is our concern with this particular feature of OK. So what is our concern with this particular symptom? Well, it turns out that an adversary can wage what we would call a reflected attack, whereby we could leverage this symptom in such a way that maybe we could construct a URL that, if clicked by a user, actually triggers this kind of behavior. But moreover, doesn't just trigger this fairly innocuous behavior like alerting the user with a message like attack just to scare them. But what if we wrote even more malicious JavaScript code that maybe steals their cookies or does something more than that? Well, how do you wage what's called here a reflected attack? Well, let's first consider what a basic link in a web page or an email looks like. It's, again, an anchor tag that starts and ends. It has an href attribute that represents the URL or file to which we're going to link the user, and then some text that the human will actually see in the web page. And now let's notice, when we correctly search for cats as we did before, that not only do we see cats in the text box here, not only do we see cats in the body of the web page, but notice now the URL. It turns out when you search for something on Google, you end up at a URL that looks essentially like this. It might actually be a little longer, but a lot of those parameters, so to speak, in the URL aren't strictly necessary. So this is the shortest possible URL that will work on Google if you want to search for cats. And notice what it is. https://www.google.com/search q equals cats. So this is to say that the way Google works is that if you want to search for cats, you simply visit a URL that looks like this. If you want to search for dogs, you visit a URL that looks almost like this, but instead has q equals dogs. Which is to say there's just a very standard format on google.com and a lot of other websites too for searching for things or really sending input to a web server. And this web form, or this text box that you typically use to type in cats or dogs or anything else, is just generating a URL that looks like this, and then Google knows what to do with it. So how can we leverage now that reality a little more maliciously? Well, let's go back to our HTML, and let's again assume that the adversary is trying to construct some HTML for their own email or for their own website in order to attack some unsuspecting users. Well, instead of the ... let's be more specific. Let's actually, in a good way, in an honest way, say that we're going to let the user click on a word, cats, which is in between my open tag and close tag. And if they click on that, they're going to end up at the legitimate Google website where it's https://www.google.com/search q equals cats. So this is correct. This is not yet an attack. But what if I am a little malicious, and instead of using the legitimate URL there for searching for cats, suppose I construct something a little more cleverly that says we're going to give them cats, but actually we're going to bring them to this URL. Now this is a bit of a mouthful, and in fact it wraps onto 2 lines this time, but notice the URL starts the same, https://www.google.com/search q equals, and then some weird text, %3c, script, %3e, alert, wrapping onto the other line, and so forth. So I dare say you're seeing some familiar phrases now, script and alert, but there's also some weird syntax there as well. Now that weird syntax is just a representation of URL escaping. It turns out that certain characters in URLs, like angled brackets and other syntax, is not good to include in URLs because it might be mistaken by the browser for something else. And so URLs typically escape punctuation symbols and other characters using this % syntax. Now, it looks a little weird to the user, but what's more worrisome is what this is going to be used for on Google's end. If the Q value equals this whole bunch of text, and it's just the browser that's encoding those special characters in this way, what Google's really going to see on its end is the actual script tag with the actual alert and the actual close script tag that you and I constructed earlier. That is to say, what Google's going to receive from that URL is no longer cats, quote unquote, but this, quote unquote, because the servers aren't going to automatically convert the % signs and those weird characters back to the original automatically. That's how URL encoding works. So what the server is going to receive is this. And again, if the server is vulnerable to naively just outputting literally whatever the human typed in, the risk is that they're going to now execute that code. And what if the code isn't just an alert? Maybe it's something like this, which still isn't in and of itself a bad thing because it's just an alert. But this is actually some JavaScript code now, alert, open parenthesis, document.cookie, close parenthesis, that would actually throw up a dialog window that shows the user the value of the cookies they have there on Google's website. Okay, not such a big deal. It's not all that different from just saying quote unquote attack. But what this means is that in JavaScript, you have access to all of the cookies for a website, at least those that are made available to JavaScript. And if an adversary doesn't use the alert function, but maybe uses a little more code to send the value of document.cookie to their own website, or to somehow send other information from the web page, the user's username, or any other personally identifying information, suffice it to say that by being able to write code in JavaScript and by being able to trick a server, like Google in this story, into executing that code, you can effectively, by transitivity, trick a user's browser into executing that code for you. So the adversary is sort of sending the code into Google, and it's being reflected back to some user if they click that same link in an email or a website. And at this point, things like their own cookies might be vulnerable. And again, to be clear, this in and of itself should not hurt you. I'm just using alert as demonstrative of what could be possible. But you could do any number of other things with document.cookie or other values from a web page as soon as you have this ability to write JavaScript that's reflected back into someone else's browser. Any questions then on this particular attack? Yeah, Harshit?
So I just wanted to ask a question about the JavaScript blockage, because many of the browsers uses to block the JavaScript, which reduces the latency but stops the browser. So how can I use the website and browser which blocks the JavaScript, but I want to access the contents of the website? So how do I access it without getting tricked into the JavaScript?
It's a really good question. And the short answer is nowadays that that's not really the best technique to just block JavaScript. The reality is, in this point in time, so many websites, most websites dare say use, if not rely on JavaScript to do any number of features or render their own content. And so it's just, I think, not realistic to just disable JavaScript in order to protect yourself from these kinds of attacks. In a bit, we'll discuss ways to mitigate this kind of attack where you disable some JavaScript, but not all. But in general, I don't think that's a realistic solution, at least on most websites nowadays. And how about another question? And if the team, could we ping again? I don't think the settings are any different today based on my forehead. Mahal?
Is there any way to change what the user sees when they hover over the link in HTML?
A good question. There used to be, yes. You could actually make the bottom left-hand corner of the browser lie and say something else. I think that has been fixed. Rungshin, do you know offhand? I'm asking a colleague here. OK, we're going to Google that and see if we can answer that definitively. But Mahal, I think that is a weakness of past browsers in years ago that has since been fixed. But keep an eye out for a text from a message from Carter. How about one more question? Tanash, if I'm saying it right?
Hi, sir.
Hello, good, thank you.
I've recently discovered a certain attack that allows website code to actually have shellcode in PHP. So this would allow them to actually open up a backdoor for the client that is visiting the website. Go against that kind of attack and prevent it from happening.
I caught part of that. Shellcode in PHP, prevent it from happening. Tanash, I didn't hear some of it. Your voice was a little garbled on our speaker. Can you type it into the chat? And I or Carter will keep an eye out?
Yes, sir.
Sorry for that. And Carter, we just have one question in the chat coming in. All right, let's turn our attention back to now some other types of attacks. So how else might these same principles be misused? Well, it turns out there's another class of attacks known as stored attacks, whereby the adversary's input isn't just immediately reflected back from the server to some unsuspecting user, as it might be when you're using the URL to contain the code. But suppose that a website were vulnerable to actually storing the user's input, even if the user's input includes HTML with some JavaScript inside. Well, that would be a stored attack, and it might work as follows. And at the risk of picking on Google, suppose that when using Gmail, suppose that if you sent someone an email with that exact same code, whereby you're just alerting, quote unquote, attack. Again, that in and of itself isn't going to hurt anyone, but it's representative of what you could do with code. Now, presumably, when you send an email in Gmail or Outlook or any other service, that email is going to be stored on a server until it's read and until it's deleted, perhaps, by the user. And if it's never deleted, it's going to stay stored on the server. So this type of attack assumes that the server might actually be saving in a database or a file somewhere the user's input. Now, suppose that here, too, Google didn't know about these kinds of cross-site scripting attacks, and they just allow you and me to input HTML and JavaScript into an email, and they just blindly save it into their database. And then, when the recipient opens this email, they just show the recipient the contents of that email. Well, what could go wrong? Well, if the recipient opens that particular email, and Google is literally rendering the script tag with the JavaScript inside, the recipient of that email, when they open their inbox, may very well suffer some kind of an attack. Again, it just says attack on the screen, but it represents being tricked into running code that someone else wrote. And in this case, someone else sent you. Ideally, what we would want to have happen instead is not have Google show us the attack message here, but rather I would like my inbox to show me the code I was sent, but not execute it. That is, just like I wanted to know that there are 6,420,000,000 cats among the search results, so would I want Gmail to just show me what it is the adversary typed in without actually interpreting it or executing it as HTML with some JavaScript inside. So that could be a stored attack and would be a stored attack if, thankfully, Google weren't actually protecting us against this, which they are. So how do you go about preventing an attack like this in software? Well, the general answer is character escapes. That is, taking any characters in users' input that might potentially be misinterpreted at best, or at worst might be dangerous to the users. Now, what characters might be worrisome? Well, in something like HTML, anything with an angled bracket, a less than sign, would probably potentially be mistaken for the beginning of an HTML tag. So I dare say that a less than sign is a dangerous character. Similarly, might a greater than sign represent the end of a tag, so that too might be something to give us concern. And there's probably a few other characters as well. So what should servers be doing? What should software be doing to avoid this kind of cross-site scripting attacks, whether reflected or stored? Well, ideally, something like this would not just be blindly outputted by Google or by Gmail, but rather it would be escaped in this very weird looking way. But let me highlight just a subset of these characters. Highlighted in yellow now are only the character escapes to which I'm referring. It turns out that this language, HTML, has standardized some special sequences of characters that represent the less than sign, that represent the greater than sign. They're a little more verbose to type. You have to type out like 4 characters in this particular case. But browsers are designed to know that when they see ampersand, LT, semicolon, they should not show on the screen ampersand LT semicolon. They should show a less than sign. And similarly, when browsers see ampersand GT semicolon, they should display not literally that, but a greater than sign. So this is to say, if Google were smart, they would take any user input you and I give them, but they would make sure to escape any potentially dangerous characters with these kinds of escape sequences, so to speak. And Google's got to look it up in a book or on a website or in the specification to know what escape they should use, but these are very well documented and standardized. And indeed, we have one here for the open script tag, and then another here and here for the closed script tag. But notice we don't have to escape all of the punctuation like the slash or the English letters in the tag name or the like. We're only escaping a certain list of these characters. Well, what is that list? Here are the 5 that minimally we should generally be escaping depending on the context. The less than sign should be ampersand LT semicolon. The greater than sign, the ampersand sign, for the very reason that we're now potentially creating a new problem. If we're using ampersand all over the place, what if the user's input has an ampersand? We don't want to confuse the ampersand in the user's input for a character escape. So there actually needs to be a more verbose way, ampersand AMP semicolon, to represent literally an ampersand. Then there's one for a double quote, ampersand QUOT semicolon, and a single quote or apostrophe, ampersand APOS semicolon. And there's more as well, but generally these are the 5 that could otherwise get you in trouble. So all of the examples we've seen thus far where Google is somehow reflecting back or storing potential attack code will not happen if Google is just smart, whereby they're escaping that input from a user before sending it back out as output to google.com search results or to Gmail inboxes. So how else might we actually prevent attacks like these? Well, we can also put in place other measures as well. And recall from past classes, we discussed this notion of HTTP headers. And an HTTP header is a line of text that's stored in those virtual envelopes that get sent from browsers to servers and from servers to browsers. Inside of the envelope, typically, is the actual request for a web page or the actual contents of, the response for a web page. But on the outside of that envelope is other information, including sorry, let me say that again. But also in that envelope is other information, namely these HTTP headers, which are, let me fix that again. Probably need this. But also in those envelopes are additional information, namely these HTTP headers, which are key value pairs that provide additional instructions, if you will, to the browser or server. So for instance, suppose that we want to ensure that this kind of reflected or stored attack isn't possible, whereby we're accidentally embedding script tags in our own website's HTML. Well, suppose that the website in question now isn't google.com specifically, but more generally example.com. And suppose that example.com's web server is configured to output always in those virtual envelopes an HTTP header that is content-security-policy : so that string of text is the key, and the value of that key is script-source, then the URL that we want to allow scripts from only. So what does this mean? Albeit fairly cryptic, if you configure a web server with this HTTP header, this will ensure that you can only load JavaScript code from actual files, typically ending in .js, that are sent separately from the server to the browser. This line of an HTTP header prevents inline script, so to speak, whereby it allows the browser to execute any old script tag in the web page. This prevents that default behavior. So as such, even if Google, even if example.com messes up and forgets to use character escapes when rendering user input that came from a URL or came from an email or any other source, this header should at least tell the browser, at least newer browsers, even if you accidentally see a script tag with some JavaScript inside of it in my web page, don't execute it. Only allow me to execute JavaScript code that came from a separate file. And let me add one quick slide here to make this clear. Oh, I did have it. OK, didn't need to add anything. It's already there. Any word back, Carter? Yeah. Ian, do we have another out-of-band way of reaching them?
We have an email out.
All right. Do we have any other way of reaching Paul or those guys?
Okay.
Thanks. It's not. It's, yeah. It can't be. Based on, I think, the symptoms. OK. Let's see how to transition this. How best to transition from the... The only type of JavaScript that will now be allowed is if I have a tag that looks like this in my HTML, which is an alternative version of the script tag. But instead of embedding any code inside of the open tag and the close tag itself, it refers to the source of, abbreviated src, some file, typically, again, ending in .js. So if this ... were the URL of a file that contains JavaScript code, that would be allowed, because the presumption there is that if someone went through the trouble of creating that file on our own server, example.com, presumably that code is safe. But what this line in our header does is it ensures that we can only execute JavaScript code if it comes from example.com in a separate file using an HTML tag like this. It will prohibit that HTTP header any script tags that are inlined in the body of our actual web pages. What else can we do? Well, it turns out, and we haven't talked about it in this class, there's other languages that you can use in the context of web pages, not only HTML, not only JavaScript, but also a language called CSS, or Cascading Style Sheets, which is generally used to style your page. If familiar, or if you take a course on web development, know that there's similarly a mechanism whereby you can specify that only CSS from a specific server, like example.com, should be allowed either, not inline style tags with which you might be familiar as well. So here, instead of script source, we see style source, which is just another way, using this HTTP header mechanism, to just ensure that the browser, at least if it's new enough, will not blindly execute script tags in the first case or style tags in the second case when these kinds of headers are present. It's an additional layer of defense against these kinds of reflected or stored attacks. Sorry. Indeed, that particular HTTP header, let's see. Let's do this. Indeed, that particular HTTP header would only allow us to include CSS in our web page if it uses a tag like this, namely a link tag with an href value, the ... of which, in this case, would be the URL of a .css file on the particular server, example.com, the relationship of which is to the page that of this thing called a style sheet. Questions, then, on this use of HTTP headers to prevent these kinds of stored or reflected attacks, or anything else thus far? Rifa, if I'm saying it right?
Oh, yeah. So I want to ask, and I see like \t and \a escape sequence deal. What is that? What does it mean?
Can you say that once more? A little trouble hearing you.
Okay. I saw something in my browser, and what do the \t and \a escape sequence do?
\p and O in the HTML. So recall that a lot of our tags, I'll use this one as an example because it's right here. A lot of our tags have open tags and close tags. And the slash, it's actually a forward slash, not a backslash. The forward slash here just finishes the thought for the browser. So this starts the tag, this ends the tag, and you use the same word, script in this case, or A or P as you described. That is what closes or ends the tag in question, so that you know where the tag ends or where the paragraph ends. Other questions? Yeah, Matteo?
Good morning, David. My question will be basically pertaining the React framework. As far as I understand, on the JSX format, you use interchangeably both JavaScript and HTML. How that isn't a security risk for this kind of attacks?
Really good question. Beyond the scope of this class for those who don't have a programming background, however, yes, React and other frameworks use a technique called JSX, which combines JavaScript with HTML with CSS that are rendered by the browser. In that case, though, Matteo, the browser is running JavaScript code that comes from the React library that is reading as input that JSX code and converting it to the resulting code that should be executed within the browser. So long as all of that code comes from .js files or .css files or the like, all is well. But if you just inline it and you're outputting headers like this, it won't execute at all. So the same rules apply. You would have to use an external file ending in .js. How about one more question before we forge ahead? Over to Adrian.
Yeah, good afternoon. I would like to ask a question about the courses. So since this is an introduction to cybersecurity, are there courses that already exist or are planned, like advanced cybersecurity or like continuation of this introduction, something like that?
So I applaud your enthusiasm, but no, there are no current plans for an advanced version of this class. We're just trying to get through the introductory version first, since we still have a lot of assignments and more to do, but maybe in the future. All right, give me just a moment to get ready. All right. So when it comes to code injection, there are other types of attacks, particularly in the context of what's called SQL, or structured query language, which is a language that's typically used with databases. So again, on a server. So let's consider how you might also trick software into executing SQL code, that is code written in this particular language when it comes to databases specifically. Well, here, for instance, is some representative code in this language called SQL, whereby you have a line like select star from users, where username equals quote unquote, and then username in curly braces. Now consider this to be pseudocode of sorts, because I'm mixing some SQL syntax with some Python syntax in this case, because it turns out that when you're using this language SQL or SQL, you typically use it in combination with some other language, be it Python or PHP or Java or something else. And you use that other language typically to construct queries dynamically based on values that humans have typed in. So for instance, if you're logging into a website and you type in your username and hit enter, very often if that website is implemented in Python or PHP or Java, it might use one of those languages to construct a SQL query that is then actually sent to the database to look up that specific user who's trying to log in. So what I have here then is mostly SQL syntax, except for, in these curly braces, some Python specific syntax. And what this curly brace with username inside of it represents is, hey server, plug in whatever the human typed in as their username into that part of the string. So the curly braces and the word username should be replaced with literally something like Malan if that is the user who's trying to log in. And that will then the resulting code will be sent to the database to select everything we know from the user's table, so to speak, in that database about that particular username. So what could potentially go wrong here? Well, it all has to do with, again, trusting input from the user. And that should now be emerging as a theme. You should generally always mistrust input that comes from users. You should do something with it, but you should sanitize it or scrub it in such a way that any potentially dangerous characters are somehow escaped. And that's exactly what the solution was to those cross-site scripting attacks, whereby so long as we escaped the user's input and changed the less than sign and the greater than sign and maybe some other symbols as well to the equivalent character escapes, all was well. So here too is an example now in the context of databases where a bit of paranoia will go a long way to keeping your software secure. Why? Well, suppose that my username is indeed Malan, but suppose that's not what I type into the website when trying to log in, for instance. So instead of typing just my username, suppose I am suspicious as the adversary that this website is probably using a database, and that database is probably using this language SQL. So what could I do to kind of mess with the owners of this website and try to trick their database into executing my code and not just their own? How do I inject code of my own? Well, instead of Malan, let me a little cryptically type this in to the website where I'm prompted for my username. Now, this does look cryptic, and odds are an adversary is not going to know exactly what to type the very first time they try to hack into a server. Rather, it's through trial and error very often that an adversary might eventually realize, this is what I could probably type into that website to inject some code of my own. So to be clear, what have I typed? I've still typed my username, M-A-L-A-N, but then I've typed a single quote and then a semicolon, and then delete from users, and then another semicolon, and then a dash dash. Now, if you don't know SQL and you are not expected to know SQL for this course, this looks weird, probably, but each of these symbols, each of these punctuation symbols in particular, means something specific and serves a particular purpose. Now, what might that be? Well, let me go back to the original query. And now let me assume that in yellow here, the curly braces with username is where my username is supposed to go. And my username is supposed to be Malan. But what if I type in that long sequence of cryptic text? Here's what's going to happen on the server. Because it's using a language like Python or PHP or Java, this yellow value is going to be interpolated. That is, replaced with whatever the human typed in. So let's do that. Let me paste in what I, the adversary, typed in. And notice I've kept yellow the user's input. So everything in white is still the part of the SQL query that the designers of the database came up with in advance. But everything in yellow is what came from like a form on the web, an adversary in my case. And this looks a little cryptic still, but even if you've never seen SQL before, you might have an intuition for what could go wrong. Because I, the adversary, typed not only Malan, but a single quote here, notice that, oh my goodness, that perfectly lines up with the single quote that the database designer used in their query. And so even though this white quote is meant to be closed by this white quote way over here, notice that grammatically in this language, not to mention in English and other human languages, this single quote here, or apostrophe, because it comes first, will be presumed to close this single quote, or this apostrophe here. The semicolon, it turns out, in this language SQL, ends a thought. It's like a period in English. And so anything after a semicolon is like a new command altogether. So notice that delete from users, semicolon, is like a second command that came entirely from me, the adversary. And then dash dash, it turns out, and this is very clever, dash dash in a lot of versions of SQL represents a comment. And a comment in a programming language means ignore everything after this. Because a problem right now is that that single quote, that apostrophe, was meant to surround the user's username. But because I, the adversary, already gave you a single quote to use accidentally as closing this thought, well, we don't need this single quote at the very end anymore. So this is why the adversary, or me in this story, is doing dash dash. That's just going to tell the server, OK, ignore everything after that, including the single quote that we do not need grammatically. So let me reformat this a bit. I'm going to go ahead and add some new lines, some white space, just to make it a little more readable. What you see on the screen here right now is equivalent to this. Notice that I've moved the delete command to its own line just for readability's sake. I've gotten rid of the final apostrophe, the single quote, because it was after a comment, which means by design it's meant to be ignored. So what I have done as the adversary, because I presumed or inferred or figured out that this website is using single quotes and they're just blindly interpolating, that is, replacing those curly braces and username with literally anything I type in, I can trick the server into finishing this first command by saying select star from users where username equals quote unquote Malan semicolon. And worse, I can trick this particular database into executing a second SQL command, which even if, again, you've never seen SQL, deleting is probably a bad thing. It's probably a destructive thing that you don't want some random adversary on the internet being able to do on your server. So what's the goal of these lines here? Well, the original intent of the first query, presumably I claimed, was just to search for the user in the database so that they could log in. So when I type in Malan and hit enter, I am somehow able to log in, probably after typing also a password, maybe a two-factor code or the like. But select star from users where username equals Malan, fine. That's probably going to retrieve the information that it was supposed to retrieve. The dangerous part here is that I trick this server into executing a second command, and this one looks destructive. Delete from users, semicolon, means delete all of the users from the system. So it doesn't help the adversary, in this case, get into the system or do anything with the Malan account other than delete it and literally every other account in the system. So this is bad. This is representative of a SQL injection, whereby I, the adversary, wrote code that you, the designer of this database, accidentally, naively treated as part of your own commands. So how else could things go wrong? Well, not only could you do something destructive like deleting data from the database, but suppose that the user is prompted at the same time for a username and a password now in this story. And suppose, therefore, that the query in the software is this: select star from users where username equals quote unquote username in curly braces, but one more phrase, and password equals quote unquote password, based on whatever the human typed in as their password. So again, to be clear, in this story, the user is prompted for a username and a password, and the SQL command that's going to use those two values looks like this. But here, too, we're setting the stage for an injection attack. Why? Because based on these placeholders with the curly braces around username and password, it looks like we're just going to blindly plug into this command exactly what it is the human had typed for their username and password, respectively. So what could a more sophisticated adversary now do? Well, maybe instead of typing in Malan and then whatever Malan's actual password is, suppose that they just want to get into someone's account, maybe Malan's, maybe someone else's altogether. What if the adversary doesn't just type Malan, not to mention Malan's password, but what if they type in this specifically for Malan's password? Now this is weird, and I'll tell you now, this is not in fact my password, but what has the adversary typed in? A single quote, the word or, then another single quote with a 1 and a single quote equals a single quote and a 1. So this looks very, very weird, but let's see what happens. And again, most adversaries wouldn't figure this out the first time they try. Odds are they'd be trying a whole bunch of techniques and heuristics to figure out what might actually work for them. So we're fast forwarding to the end of the story where the adversary has figured out that this weird sequence of characters can hack into this server by tricking it into executing code that wasn't intended. So here again in yellow is exactly what the adversary has typed in. Malan, which may very well be a legitimate username, but then for the password in yellow, single quote, or single quote 1, single quote equals single quote 1. And based on our previous example, you can perhaps see what's starting to go on here. We've finished the Malan thought naturally, like we didn't type anything malicious for the username this time, but we did type something seemingly malicious for the password. And the first single quote in yellow quickly finishes the password thought, quote unquote, nothing in between. But then we're saying or, quote unquote, 1 equals quote 1. Why? Well, the adversary in this case kind of figured out or knew or guessed that the SQL command ends with a single quote itself. So the whole point here is, even though this too probably looks very cryptic, is that grammatically what the adversary has typed in not only perfectly aligns with the username field because it's just Malan, nothing special there. But very cleverly, the adversary has finished the thought of this single quote and also finished the thought of this single quote. So we've made everything balanced, just like you would not only in SQL, but in a language like English. So let me go ahead and clean this up a little bit too to make clear why this is dangerous. This command now, once formed by the server based on that adversary's input, is really the same as this. And I'm just going to add, again, a new line and some white space just to help us wrap our minds around what's going on. So I've just moved the OR line to the bottom. And just like in math class years ago, let me go ahead and put parentheses around things here that makes clear what the precedence is of things like and OR. It turns out that and, like multiplication, binds at a higher precedence. It's more important. You're supposed to do it first. So I'm going to add parentheses now to this first expression. They're not strictly necessary. They're implied. I'm just making them explicit now to show you, just like in math class, the order of operations. Now, what does this mean? This means that the database is going to say select star from users. So select everything from the users table where the username is Malan and the password is quote unquote. Now, that is probably not my password. My password is definitely not nothing. It's not empty. But that doesn't matter now. Why? Because even if this first clause, where username equals Malan and password equals quote unquote, even if that doesn't find anyone in the database with the username of Malan and a password of quote unquote, it doesn't matter because we've tricked the database command into including an OR, which is so stupid that it's always true. Or 1 equals 1. Well, 1 always equals 1, which means that now, logically, this query is going to return everything we know about users from the database. And why is this problematic? Well, when you're logging users into a database, logging users into a website or application, you're typically searching for them in the database. And typically, if you get back one or more users, you're going to assume that the very first user is the one that you want. And maybe in this case, it's Malan. But it's also very common in servers for the very first user that was created to be you, the person that designed the site. And you probably have administrative privileges. That is, access over everything in the system. And so if a query like this is returning all of the users, including you as the very first one, if there's additional code in the system that we won't put on the screen here or bother hypothesizing about, it means that you could be now letting the adversary log in maybe as Malan, but worse, maybe as you. All because you trusted user input. But you should never trust that your users, if called Malan, are going to type in just Malan. You should always assume that there's someone out there, very annoyingly, very maliciously, that's going to try using some single quotes, some semicolons. Or in HTML, we saw a less than sign, a greater than sign. You should always expect that someone on the internet will have enough time and interest in hacking your website or application that this might indeed happen to you and your software. So what's the solution then? How do you avoid a query that's equivalent ultimately to this? Because if there's no Malan with no password, it's still the same as asking for where 1 equals 1, which is anything. And to be clear, I didn't have to use 1. I could have used 2 or 3 or 4. I could have used cat or dog or anything else, so long as the thing on the left equals the thing on the right, and I type that into the application. The same thing would certainly equal itself, is the point here. And 1 is just the simplest thing we could think of. So what is the solution here to SQL injection attacks specifically? Well, it's very similar in spirit to the notion of character escapes. But in the world of SQL, there tend to be standard ways of escaping dangerous characters. You don't have to do it yourself. And much like security in general, with encryption specifically, you probably should not be writing code yourself to solve problems like these that hundreds, thousands, millions of people before you have already had to deal with and have probably solved correctly. Do not reinvent wheels when you don't need to in the context of security. So this is to say, in the world of databases, most databases support what are called prepared statements, which is a fancy way of saying that you provide the code for your SQL query, you provide placeholders for wherever you want user input, but let the database itself replace or interpolate those placeholders with the user's actual input, and let the database handle escaping anything dangerous. And we've seen that things are dangerous like apostrophes thus far. So for instance, instead of writing a single apostrophe, and this is weird admittedly, in the world of SQL, the way you typically escape an apostrophe is not like HTML. You don't do ampersand, APOS semicolon. You don't, like in some languages, put a backslash in front of it typically. The way, weirdly, you escape a single quote or an apostrophe in SQL is very often by putting two of them in a row. So why, we'll defer that to another day, but this is just the convention. Now, this means that you could write code that changes any single quote to two single quotes, but again, don't bother doing that. Use functionality that comes with the database or whatever library you're using. So for instance, if we go back to that very first query that was vulnerable to being injected with something like delete from users, what if we now do this? Let's change our Python-based placeholder using curly braces in yellow here. And let's change that and get rid of the quotes and just put a question mark. This is one of the common conventions in prepared statements where you put a question mark, not because you don't know what to put there, but because you want the database to replace that question mark with a user's own input. Then what happens? Well, if the user types in that dangerous command with the delete inside of it, notice what happens. Here's the single quote. Here's the closed single quote. And the database has given that to you automatically. The prepared statement adds those single quotes for you. Notice that even though I, the adversary, only typed in Malan single quote semicolon, the prepared statement has gone ahead and escaped a single quote or apostrophe with two of them instead. And nothing else here thereafter is actually too worrisome. That alone is sufficient to solve the problem. Now, this looks a little weird, right? Because it kind of looks like logically, well, you still have this quote and this quote which line up, and you still have this quote and this quote which line up. So it looks like we haven't really fundamentally solved the problem, but we have. It turns out in SQL databases, anytime they see two single quotes back to back, they don't try to pair them with something to the left or something to the right. They just treat it as one special escape sequence, so to speak. So that would then fix this query. And if we go back to the second query, which had two placeholders, username and password using this Python syntax, let me go ahead and change that to prepared statement syntax using, in this case, question marks without quotes. Let's let the database do all of the escaping and the quoting for us. And now if Malan tried to log in with that other malicious command, it's going to look like this. Malan quote unquote, and that one's always been fine. And then in here, this one looks a little weird, but now we have quote, quote, or, oh, wait a minute. Damn. Let me think for 1 second. R1 equals 1. Ah, bug. Sorry, let me fix this. Carter, do you mind telling folks we'll be back in a sec? OK, Mike is still live? So this is actually, we'll fix this in a moment. This is exactly why like you always use third-party libraries to escape your code. Because like literally, I made this slide by hand, sort of manually escaping things. And even I screwed up on the slide. So what was missing before were extra quote marks. Now I've gone ahead and added them. But again, perfect lesson as to why you should never trust yourself to solve security problems if someone else has solved them properly beforehand. So let me try to fix this and pretend that it was right the whole time here. OK, and let me just see where we're going. OK. OK. Let's now consider that second query, which had two placeholders, one for username and one for passwords, and see how those would be handled now if we use a prepared statement instead. Well, I would propose that instead of using that Python syntax with the curly braces and our own quotes, let's again just use a question mark here and a question mark there, and trust that the database itself will add any necessary quotes and escape any potentially dangerous characters. Now, what did the adversary type in that second scenario? Well, it was just innocuously Malan, and so that comes back from the prepared statement as being prepared with quote unquote on the outside. No problem there. But this other input from the user, from the adversary's password, which was very cryptic with lots of single quotes, notice that every single quote in the adversary's so-called password has been escaped, so that the single quote here becomes 2. 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 And the prepared statement automatically adds a final single quote at the very end. But I've kept highlighted in yellow everything that represents the user's input now that it's been properly escaped, because again, even though you might try mentally to pair this quote with this one with this one, this one with this one, and so forth, that's not what the database does. Whenever it sees, in this case, 2 apostrophes back to back, they are treated as special escape sequences. And so the only quotes that ultimately are treated as lining up are the 2 around the username and the 2 around the entire password here. So the characters are still in there, but they've been escaped, sanitized, or scrubbed, so to speak, in such a way that now the database is smart enough not to mistake those for quotes that should be matched with ones that we might have otherwise written previously. Now there is another class of attacks that similarly involve injection into your software, particularly command injection. Those of you familiar with a command line interface in the context of a terminal window or the like might be familiar with how on a system you type commands as opposed to always using your mouse to point and click on menus and buttons. The problem with command injection is that it's all too easy in a lot of today's programming languages to write code that invokes commands on systems, whether it's to copy files, delete files, move files, execute other commands altogether. And that's because a lot of programming languages come with functions. That is a feature called system, which is literally a feature of some programming languages that allow you in your program to execute a command on the underlying system, a command on the underlying operating system. And that might be useful for you because in addition to writing your own code in some higher level language, you can occasionally run a command on the system itself. But the problem is that if you, the programmer, somehow take user input and you just blindly pass that user's input to the command line, so to speak, to the terminal window, to the underlying operating system, that is yet another context in which potentially dangerous characters like semicolons or the like could accidentally finish your thought, but then start a completely new one from the adversary, so that they too on your system can not only delete things like data from your database, but even files from your file system. They could perhaps send email or spam or do anything in a command line environment that you yourself could do on the same. In other programming languages, the same idea exists in the context of another function called eval, which evaluates whatever you pass to it. So there too, if you're in the habit of using system or eval, taking user input and passing that user input as part of the input to system or eval without having sanitized it or scrubbed it or more generally escaped potentially dangerous characters, you're putting your entire system at risk and any and all software that's installed on or running on the same. So what's the solution here? In any of those programming languages to which I'm alluding that have functions like system or eval, they almost always come with another function or built into these functions, a way of escaping the user's input. So I would always take care to read the documentation if you yourself are or want to become a programmer, that whenever you take user input, you always figure out and think to yourself, wait a minute, how can I escape this properly so that I can't be tricked into executing some command, some SQL, or some HTML and JavaScript within my own software? All right, that's been a lot. Let's go ahead here and take a 5-minute break. And when we resume, we'll look at a whole other category of potential attacks on software. All right, so we're back, and let's consider another class of attacks that also relates to this. Do we want to say that? Sorry. Sorry, let me get my thoughts better. OK, sorry. Ready when you are. All right, we're back. Let's go ahead and return to this world of HTML and the web, if only because so much of today's software is actually web-based. And indeed, even on your Macs or PCs or phones, what looks like a native application, so to speak, might actually still be implemented in HTML with that other language, JavaScript and CSS. Well, it turns out in the context of a browser, there's very often a feature called developer tools. And indeed, if you've done any web development of your own, you might have played with this feature. And these developer tools, which might be called something slightly different across different browsers, allow you to poke around the HTML, the CSS, and the JavaScript that compose some web page, either that you yourself have made or that someone else has made and you have downloaded or accessed via your own browser. Let's consider now, though, what you can do if you have access to these developer tools. So for instance, here is some HTML using a tag called input, which would create a checkbox on a website. We haven't seen this one yet, but it's similar in spirit to the paragraph tag and the anchor tag, in which case it is interpreted as the browser as meaning, hey, browser, here comes a checkbox. The only thing different that's worth noting here is that some HTML tags don't actually need a close tag. Because whereas a paragraph starts somewhere and then ends somewhere else after some number of words, a checkbox is either there or it isn't there. So there's really no conceptual notion of it starting and stopping. So some HTML tags don't even need end tags or close tags. This, then, is one of them. This, then, is an input tag that gives us a type of input, namely a checkbox. And another curiosity about this is that some HTML attributes don't need values. We saw the href attribute for the anchor tag earlier, and that, of course, had a value. In quotes was the URL that you want to link to. Here we see that same paradigm, type equals quote-unquote checkbox, to give us specifically a checkbox type of input. But you'll also notice here another attribute, specifically for this input tag, that's literally called disabled. And strictly speaking, you don't need to give it a value because it's either there or it isn't. And if it is there, that just means that this checkbox is exactly that, disabled, which means you can see it, but it's not checked and you can't actually check it. It's disabled and lightly grayed out typically on a browser. So why might this be? Well, maybe there's some feature in the browser that you don't want to give some users access to. Maybe based on who has logged in, they should or should not have access to some feature. The problem, though, with HTML and CSS and JavaScript, or really anything that is web-based or using those languages, is that you're sending this HTML to the user's own device, to their browser on their phone or laptop or desktop, which means they can not only see this HTML code, but theoretically they can edit it. They can't edit it on the server because that's your own copy, assuming they can't hack into the server, but they can edit their own copy thereof. Now, usually that's not such a big deal because what's the worst that can happen? They can hack themselves by changing HTML on their own computer or phone. But it is problematic if you are using HTML or even JavaScript to try to prevent certain user interactions with your server. So for instance, if you simply don't want a user to be able to check this box so that when they submit a form, they're not agreeing to something or they're adding something to their shopping cart by using this checkbox, well, you might rely, therefore, on this HTML attribute disabled. Just prevent them on the client in the browser from checking this box. But it turns out with developer tools, which are accessible usually via a menu at the top of the screen or by right-clicking or control-clicking on a web page and then selecting an option, a user with access to HTML can change any and all of that HTML on their own computer, which means they could just remove this disabled attribute in their own copy of your HTML on their computer and effectively enable that checkbox by getting rid of it. Now, what does this mean? Well, there's no problem yet, but if they do now check that checkbox, and you didn't want them to be able to, and they submit the checkbox to the server as by clicking a submit button in a web form, you on the server if you're not paranoid enough, might just trust that if I see a checked box being submitted via form, they must have been allowed to do it, so I will trust them. But no, here too is an example of where you should never trust users' input, because if you're trying to disable them from doing something on the client, they don't have to respect that. They can override the HTML in their own browser, remove any such defenses, and then send the checkbox to you anyway. What else then might they do? Well, okay. The takeaway here, then, is that you really should never rely on client-side validation alone. And this disabled attribute is just one minor incarnation of that, where you're relying on the client to ensure that the button is that the checkbox is disabled and its value can't be sent to the server. But client-side validation is really on the honor system only, because if someone knows how to use these developer tools and removes the disabled attribute, or if they know how to use developer tools and maybe disable JavaScript altogether for your website on their computer, any form of client-side validation in HTML or JavaScript that you wrote on the server, but that your server sent to their browser and that's therefore executed by their browser, is vulnerable to simply being turned off. So the catch is that even though client-side validation tends to be nice in terms of user experience, the button is obviously disabled, so I should not be able to click on it. Or my email address is improperly formatted, so I should not be allowed to submit the form. Any forms of client-side validation tend to give the user immediate and often very useful visual feedback. But if it's not accompanied, this client-side validation, by server-side validation, your server software is still vulnerable to attack in some way. So what other form might this take? Well, here's another example of an HTML input. This time it's of type text, which means it's a text box on the field. Suppose that you really want them to provide that value. Maybe this text box represents the user's name or their email address or their password or something like that. And so if you know a little bit of HTML, you know that there's not only a disabled attribute available to you, but also a required attribute. And it doesn't have an equal sign or a quote mark. You don't need that. It suffices just to say this input is required. But the catch here is too, if a user doesn't want to give you a name, doesn't want to give you an email address, doesn't want to give you a password or some other value, well, they can use these so-called developer tools, click a button on their browser, remove the required attribute, and voila, now they do not need to submit that value. Now, that in of itself is not a problem, because again, they're only hacking themselves. But if they're then allowed to submit this form to your server, and your server just trusts or assumes that every user will send you a username, an email address, a password, or the like, that's where things can break. If you're trusting client-side validation alone to ensure that the user's input is as expected. So if they're allowed to get rid of something as simple as this required attribute, effectively making the input like this, you might be missing some value, and so you must, therefore, use server-side validation again. And we won't get into the particulars of how you do this, because it will completely depend on the type of server software you're using, the programming language that you're using. And so it's really the principle today that's important, that client-side validation, whereby the browser or the user's own copy of your software tries to preempt mistakes and require or disable certain inputs, that's fine. That tends to give good, immediate, useful user feedback. But it must still be always accompanied by server-side validation, so that you have the final say over what the user input looks like and if and how it's actually stored into your system. Again, the particulars of how you do one or the other is the topic for an actual programming class or a class on web development specifically. But for now, it's this principle. Just because you have client-side validation doesn't mean you shouldn't also have server-side validation. And in fact, if you've got to choose one or the other, always choose server-side validation. Client-side validation is really just icing on the cake. It adds to the experience, but it's not the prerequisite one. Questions then on these so-called developer tools or these kinds of threats when it comes to validating the user's input? Yeah, Utkarsh? Utkarsh?
Yeah, so my question is more related to SQL and command injections for a second.
OK.
About that, isn't it really easy to just not run the user's commands with admin or root privileges to delete certain records from a database or something? Wouldn't it be
Yes,
more
another
secure?
defense would be to make sure that whatever username you're using to execute these SQL commands does not have the ability to delete anything at all. However, some threats only need select access. So the second example I showed you, whereby we trick the database into just selecting star from users where 1 equals 1, that was an example of one where permission-wise it probably would work, and it might allow the adversary still to log in. But your suggestion is a good one as an additional defense, not an alternative. Other questions? Yeah, Natalie?
Hello, good afternoon. Would it be possible to do a seminar on server-side validation for those who are taking CS50 web?
A good question. We will make note of that. I'm not sure we'll have plans too soon, but that's a good suggestion for that web class specifically. And Carter, for those unfamiliar, if you want to paste the link of CS50W into the chat. How about one more question? Bhavik? Oh, still muted.
Can you hear me now?
Yes.
Yeah. So, like, there are some. Suppose I want to send some email from form, right? So there are some libraries like email.js that doesn't require like server side. So if I disable some fields using that library, would it be still sending some emails?
Can you say that again? What is the server doing for you?
So like email.js is one of the libraries that allows you to send email through a client only. You don't need a server. So does that library would handle such validation cases and all?
Oh, a good question. I don't know. It would totally depend on the library. And if it's sending emails somehow, it's either has to be going through some server or it has to be using your own computer somehow. So it's tough for me to say without seeing. I would check their documentation, if anything. All right. Okay. All right, so let's take a look at one final threat specifically in the context of the web, namely HTML, and it's, let's see. All right, so let's look at one other threat specifically that relates to the web, and HTML specifically, and this one's more of a mouthful, but this one is called cross-site request forgeries, abbreviated typically CSRFs. So what is this attack? Well, let's consider, for instance, the following. It turns out that there's at least two different ways that web browsers can make requests of web servers. And if you've taken a programming class or web development class, you might be familiar with the most common of those, namely get. Get is actually literally an English verb, and technically it represents one way that information can be gotten by a web browser from a server. Specifically how? Well, in the context of get, the browser puts all of the information necessary in the URL that it sends to the server. So for instance, Amazon, at least in the US, has a feature whereby with a single click of a button, you can buy something now by clicking a button, and embedded in that button essentially is the unique identifier of that product so that you buy that product and not some other. This is to say you don't need to manually add that item to your shopping cart, check out, type in your payment information or the like. Literally, when you go to a products page, if you've configured your account already, you can click buy now and boom, you have bought that product. Now, for that to work using this technology called get, which is an HTTP verb, it's a way of getting information from a server or to a server, you can literally use a link as simple as this. Here's our familiar anchor tag. Here's the close anchor tag over here. And notice what the human's going to see in this story is literally, quote unquote, buy now. So how might Amazon be implementing those buttons? Well, they could be, if using get as the operation, simply have an href value that equals something like this. https://www.amazon.com/dp/b0. This is the wrong one. Sorry. Sorry, I have the wrong HTML here. Let's go ahead and take a slightly early break. Well, we'll be back in about 5 minutes. My apologies. Let me fix this so we don't have to refilm this part. See you in 5. Sorry about that. We will resume in a moment. And in a moment, we'll dive back into these cross-site request forgeries. Then in a few minutes, I'm going to pretend like we're going to take a break because I don't want to waste people's time by taking more breaks than we actually need. So I'm going to say, let's go ahead and take a break. And when we resume something, but then we're not going to actually take a break for more than a few seconds. So don't disappear if you'd like to continue following along. All right. OK. Let's consider another class of attack to which your code might be vulnerable if it's on a server using the same language, HTML, namely cross-site request forgeries, or CSRFs. So this one's more of a mouthful, but it too relates to a mistake you might otherwise make when writing software on a server if you're not already familiar with this kind of threat. So first, HTTP, recall, is this protocol, this convention via which web browsers and servers communicate. Well, it turns out there's different ways that browsers can get information to a server, and one of those ways is literally called GET by convention. In other words, inside of that virtual envelope is typically literally this word, GET, followed by the file name that the browser wants to get from a server. But more importantly for our purposes is that whenever using this GET method to send information to a server, all of the information that you want to get is embedded in the URL itself. So what does that mean? Well, consider, for instance, this sample link in HTML. Here's my anchor tag beginning. Here's my anchor tag ending. Notice here is the text buy now. Well, let's suppose that you're in the US here, and on Amazon.com in the US, there's actually this feature where you can buy now. That is to say, when you visit the page of a product on Amazon's website in the US, if not beyond, you can skip the steps of having to add an item to your shopping cart and check out and choose your payment method, and then some number of clicks later actually buy the product. Rather, if you configure your account in advance, you can go to any product's page, literally click a link or a button that says buy now, and that's it. In a single click, for better or for worse, that product will be shipped to your home. So how might Amazon be implementing this? Well, they might indeed be using a link like this, the href value of which is a URL, like https://www.amazon.com/dp/b07xlq2fsk. In other words, that seems to be enough information in the URL alone via which to buy the product whose unique identifier is apparently that string of text at the end. Now, that's all fine and good, and that actually seems very user-friendly, because with a single click on buy now, I can indeed buy that product. But the danger here is that if this link is not just on Amazon.com, but is in some adversary's website, or maybe in an email that is sent to you, if it's that easy to buy something now, you could trick someone potentially into buying things that they didn't actually intend in this case, or doing anything else on a web server into which they're already logged in if GET is the method being used to get something from that server. Well, why is this exactly, that this URL is problematic? Well, consider, for instance, the following HTML instead. Suppose that you visit an adversary site who just likes to create havoc in the world, and that adversary site doesn't even have an anchor tag or a link that they want you to trick, so it's not even as deliberate as a phishing attack that they want you to click some link. Suppose they're using something like an image tag, which it turns out in HTML, IMG for short, is how you embed an image on a web page. And how do you specify what image? You specify the source thereof, src for short, the value of which can be the URL of or the name of the image you want to display. But strictly speaking, that URL doesn't have to actually lead to an image. It could actually lead to an Amazon product page. But the way images work on web pages, recall, is that typically when you visit a web page, the images automatically load. You don't have to click or do anything typically for the images to appear on a web page. Maybe in emails, and that's an anti-phishing mechanism, but in web pages, you typically don't have to click on anything to see the images. That is to say, the value of these source attributes are just automatically downloaded and displayed to the user. Now, this, in fairness, is not an image, but the browser doesn't necessarily know that from the get-go. And so if this HTML is in some adversary's website that you've somehow been tricked into visiting, and you don't even click a link, you just visit that web page, that means this image tag is going to try to download this source, and even though it's not going to get an image, it is going to buy that product for you. Why? Because if you're logged into your Amazon account, even though this is in another tab, it's as though your browser requested that URL via that GET method, because all of the relevant information for buying that product is in the URL alone. So it turns out that using GET is actually not a good thing when it comes to changing state on the server. To get technical, the GET method is meant to be safe. Safe whereby it does not change any state or values on the server. So it would actually be incorrect, or definitely bad practice by Amazon, if they were implementing their Buy Now button simply with a simple URL and a simple GET request. It should not be that easy to buy things on the internet, let alone change state on the server in other ways. So there are thankfully other methods, but even these are potentially vulnerable to this kind of attack. There's a post method, which is typically used by browsers when you want to post your credit card information or your password to a server. You don't want your credit card, you don't want your password typically ending up in the URL of your browser for privacy's sake. So rather, post will kind of hide it more deeply in that virtual envelope to which we keep alluding. Post might also be used if you want to upload images or video files to a server, because those don't really fit in URLs, it would seem. And so post is an alternative that is meant to change state on the server. For instance, buy products for you. But even this can perhaps be abused. Well, let's take a look how. Here is now some HTML, and it's more HTML than we've seen thus far, but we'll wrap our minds around each piece of it, that represents an alternative implementation of the Buy Now button on Amazon that's no longer a simple anchor tag with everything that's needed in the URL. This is more of a traditional web form. And it's fine if the form is super short and only has a single button. It doesn't need text fields or anything like that, but there's a lot going on here. So let's see. So here's the form tag, the opening tag. Here's the close tag. So everything in between must be implementing this form. The action of this form, I claim, is going to be to submit the information to this Amazon.com URL here. But the method that we're going to use is explicitly post. So it turns out in an HTML form, if you don't specify a method, it will use GET by default. So explicitly, I'm at least using post because I don't want everything to be in the URL alone. Well, I've got two inputs here, one of which is of type hidden. Well, what's going on here? Well, it turns out that in HTML forms, you can create like key value pairs to send input to a server. So if you recall previously, I used the DP part of the URL as separating Amazon.com from the product ID. And here, and now I'm making this up for the sake of discussion, I'm supposing that Amazon supports a web form name called DP whose type is hidden, because it can be, the user doesn't need to see this, but the value is that same product ID. So this is an alternative to embedding that product ID in the URL. Instead, I'm saying there's an HTTP parameter called DP, the value of which will be this. But it's hidden, so the user doesn't even see it, which is fine, because the whole point is a nice, simple Buy Now button. How do we get that button? We use a button tag in HTML, the type of which is to submit, because its purpose in life is to submit this form. And the text that the user sees for this button is indeed Buy Now. So what am I doing? This will make more sense, admittedly, to those of you who've already studied a bit of web development, who have written HTML yourself. But I'm essentially making it harder for an adversary to automate an attack on a user's Amazon account. Why? Because I am not just using a link anymore that the user might click, or a URL that could be subtly hidden in an image tag. Now I have an actual web form. And at least based on my naive understanding of HTML at the moment in this story, this would seem to require that a human click an actual button. Like, I cannot use this as the source of an image. It's not a URL. It's all of this complexity. So if you're familiar with GET versus post, you might be inclined to think that, OK, post surely solves the problem by using this web form, because you make sure in this way that someone clicks the button before they can buy anything. Now, why is that indeed naive? Well, it turns out using not just HTML, but this language we've seen a little bit of today, namely JavaScript, can be used to automate the process of submitting a form. So if an adversary now has this HTML in their website, they don't have to wait and hope that someone like you or me is going to come along and click the button explicitly, because that would be a little weird to click a button thinking you're going to buy something now, but it's not on the actual Amazon.com. That alone doesn't matter. If the adversary can just trick you into visiting their website, and their website contains this HTML and this additional JavaScript, they can immediately submit this form for you to Amazon without you clicking a thing. Why? Well, inside of this script tag that I've added down below, I've simply said document.forms bracket 0. So this means get me the first form on the page, and I'm presuming there's only one in this story, and then submit it. So this is to say, in JavaScript, not only can you do things like trigger alerts on the screen, those dialog windows, you can similarly, through code, automatically submit forms. So it doesn't matter that you're using post. It doesn't matter that you have an actual button that must be clicked. It doesn't have to be a human that clicks that button. It can be their browser automatically executing this JavaScript code in the adversary's website that just submits that form for them. So this is the essence now of a cross-site request forgery. If HTML like this exists in the adversary's website, some other website, you can nonetheless trick users into executing operations across websites, on Amazon.com in this case, even though the users themselves are not on Amazon.com. So that's the cross-site aspect of these attacks. And it's a request forgery in the sense that it's sending all of the right information, but it's forged by the adversary. It's not coming from the Amazon.com developers themselves. But it is this simple, because if Amazon does not defend against this attack, there is nothing stopping you or me or any adversary from including code like this on our websites, somehow tricking users into visiting our websites, and boom, having products sent to them automatically, assuming they have an Amazon.com account and they're also already logged into it in another tab, or at least earlier in the day, for instance. So how can we now mitigate this attack and threats of code like this? And actually, let me pause here. All right. Any questions now on this particular attack, these cross-site request forgeries, whether implemented using GET with simple URLs, or even implemented with POST using actual forms? Rifan?
If the example before is only the get method, what if there is a $sign get, it becomes $_get?
Good question. You are referring, I believe, to a JavaScript library called jQuery, which includes a function called $.get, which will mimic a GET request. Same exact thing. I'm just using HTML to keep things relatively simple. You can implement these CSRFs using JavaScript as well, including that function. The JavaScript fetch function can be used as well. Other questions? Sundar?
Sir, my question is, how can AI model and quantum computing change the way that we look at cybersecurity?
Quantum computing? Let me address that another time, because I dare say that's a bit far from today's goals. But quantum computing is bad if the bad guys have it and you and I don't. I'll put it that way. It's only a fair fight if we all have access to the same. All right, so give me just a moment and we'll turn our attention back here. All right, so how can we defend against this threat even when there's JavaScript code automatically inducing submission of these forms which have enough information in them in order to buy something on our behalf? Well, it turns out that we could include something like a special token. And it turns out a common way to address this problem is by having the server not just output a simple HTML form, but to output an HTML form that additionally has another value, often hidden as well. And by convention, in some worlds, it's called the CSRF token, which is just a fancy way of saying an extra value. But its value is typically meant to be random. And I've chosen something fairly pronounceable here, 1, 2, 3, 4, A, B, C, D. But assume that that value is randomly generated by the server. And it might have a bunch of numbers, a bunch of letters in it. But the point is that it's randomly generated by the server. Now, why is this important? The implication of this mechanism, by having a web server output not only the product ID and also the button inside of a form that they might be using to implement this buy now feature. The point is that the server should also be generating some secret randomly generated piece of information in that server as well, in that HTML as well. And the server should remember that value as by using its own database or some other mechanism. The point here, though, is that only the server, Amazon.com in this case, knows what that value should be for you, a specific user. And so an adversary, even if they trick you into visiting their website where they have HTML that looks quite like this, the adversary, unless they've hacked Amazon.com, which is not part of this story, they would have no idea what this random value is that Amazon.com is using for your buy now buttons. Because again, if it's just an adversary on the internet, they haven't taken over Amazon.com, they haven't taken over your computer itself. They are just trying to trick you into visiting a web page of their own that has HTML like this. They won't know what value to put there. Now they can try to guess, and maybe they could guess 1, 2, 3, 1, 2, 3, 4, A, B, C, D. But assuming it's more random than that, the odds that that adversary guesses your CSRF token value is just so small and low probability that it's just not going to happen realistically. So now, even if you visit a web page that contains this HTML, even if it has some JavaScript that automatically submits the form, because the adversary doesn't know the value of this CSRF token, Amazon.com can just ignore the request to buy that product now. And they can throw up an error message or say something went wrong or the like. But the point is that only the real Amazon.com should be able to generate and remember this CSRF token value. And so therefore, they can validate server side that it's indeed you who intends to buy something now. The adversary, if they put a blank value there or any other value, it's not going to be validated server side because the server realizes, that's not the value I'm using for David. That's not the value I'm using for you. So this is a very common technique. It does require a bit more complexity on the server. Very often, programming languages like Python will come with libraries, third-party libraries or code that other people have written that allow you to add this functionality to your own software. But you have to know that the threat exists, and you have to look for a solution there too, or implement it yourself if need be. But almost always is a library the answer to this problem. There's another way you can solve this same problem, which doesn't involve outputting any HTML at all. It can rather be sent via tokens instead. So if you were to use JavaScript as the language via which you're sending requests from a browser to a server, as is very common these days for the most interactive of websites, you don't have to even use HTML. You can instead use an HTTP header instead to send that same value. So that is to say, if there's no web form per se for a human to submit because it's JavaScript code in a page that's interacting with Amazon.com, well, the browser using JavaScript can send a request that looks a little something like this, the point of which is that it can include as an HTTP header that value. And this is something that an adversary definitely cannot send because this header is meant to come from the browser, not from the server, which is to say, even if the adversary has their own server, it's your browser that's going to be sending this token. And so even then, well, sorry, I misspoke. Let me rewind for a second. Now, there is an alternative way to say it. Now, there is an alternative way to send these same tokens. It doesn't actually have to be in the HTML of the page. It is also possible to send these kinds of tokens as HTTP headers as well, as might commonly be the case when a website is very heavily using JavaScript and is using JavaScript to talk directly to a server without even any HTML. Well, the same values can be sent via this other mechanism as well. So if you're interested in these kinds of web-centric attacks especially, you might find it interesting to explore the Open Worldwide Application Security Project, which has documentation of, discussion of, recommendations for all of these kinds of web-centric attacks and more. For now, though, let's go ahead and take a short break. And when we come back, we'll look at problems that go beyond the world of the web, specifically the software that you might have running on your own Macs, PCs, or phones. OK, remember, that was just a fake break. We'll resume in just a few seconds so that we can keep on schedule. Only a little bit more to go. All right, we're back, and let's now consider a class of attacks that relate to arbitrary code execution, which is a fancy way of saying enabling. All right, sorry, let's do that again. All right, we're back. Woo, don't know where that came from. All right, we're back. Let's now consider a class of attacks that is particularly common when it comes to software that's running on your own Mac or your PC or your phone. So not web-based, but local instead. And the first of those is generally called arbitrary code execution. The potential for an adversary to somehow trick your own computer into executing code that you, the adversary, have written and that's not embedded in the actual software that's meant to execute it. This is an example more generally of what might be called remote code execution, whereby the same attack can happen even if the adversary is somewhere else in the world, perhaps connected to you somehow via the internet. And how might these attacks be possible? Very, very common mechanism for waging these kinds of attacks, whereby an adversary tricks your own system into executing code that the adversary wrote, is through something generally known as a buffer overflow. Now, to be fair, this is a topic you would explore in more detail in a class on programming specifically, computer science more generally, but we'll give you a high-level sense of what the threat is as it relates to software that might very well be running on your own computer. So what is a buffer overflow? Well, for this, we need a mental model for what's going on inside of your computer when running a program. And when you double-click a program on your Mac or PC or your phone, and it opens up and loads into the computer's memory, the memory you can think of as this big rectangular region that represents all of the bytes or megabytes or gigabytes that are in your Mac, your PC, or your phone. And the computer, or device more generally, uses different parts of this memory for different purposes. And this is just because humans came up with conventions years ago to lay out the computer's memory in this way, using some of it up here for one purpose, using some of the memory down here for another purpose instead. So for instance, if this big rectangle represents your phone or your computer's memory, let me just propose that at the top of it, so to speak, although memory doesn't have a top, bottom, left, or right, because it totally depends on how you're holding it, but assume conceptually that at the top of your computer's memory is the machine code for the program you're running. So long story short, when you write software, at the end of the day, zeros and ones are involved. And the zeros and ones represent the instructions or commands that that software wants to execute on your computer. When you click an icon or double-click an icon and load a program into memory, the actual program's machine code, the zeros and ones, if you will, are stored up here in your computer's memory. Meanwhile, while a program is running, it might need more or less additional memory as it executes instructions therein. So what does this mean? Well, if the program is prompting you for input, or if it needs to load a new level from a game, it might need more and more memory, but eventually it might not need that memory anymore. So the memory requirements of a program tend to go up and down all the time based on what you, the human, are doing with the software and based on what the software is designed to do. So computers typically use this bottom area of the computer's memory for a so-called stack. Very similar in spirit to any physical thing that you might stack one on top of the other, like clothes in a closet or trays in a cafeteria. Stacking means literally from bottom on up. But the weird thing is about a computer's memory is that by convention, when the computer needs memory, it first uses some memory from the very bottom. And then if it needs more, it uses more above that. When it needs more, it uses more above that. So instead of just going top to bottom, it actually deliberately by design goes bottom up for reasons we won't get into in this course, but just take on faith that indeed this stack of memory grows upward. The catch, though, is that sometimes software doesn't necessarily know in advance or predict correctly in advance how much input you, the human, might give it. So for instance, a computer program might decide to take up this much memory at the bottom, but then not realize that, oh, wait a minute, what if the human types in a really long name or a really long essay or just gives me more keystrokes as input than I, the programmer who wrote this software, anticipated. That might mean that even as you allocate what are called frames of memory on this stack, the user's input might not stay confined to that particular frame. If they type in too many characters at their keyboard, what's supposed to go here might end up going down here. So overflowing these frames of memory. So the computer or the programmer makes hopefully an educated guess as to how much input the user might have. But if they're wrong, that input might be too tall and therefore overlap other parts of the computer's memory. Now, there are ways to defend against this. So the scenario we're worried about here is often when programmers don't know how to anticipate this, or when you are using software written by programmers who didn't anticipate or implement the solution properly. So what might go wrong? Well, for instance, when a program first starts running, one of the first things it does, if it's calling another routine or another function, when you click on a button, when you start typing keystrokes, the computer might start using some of this memory, and it might be moving around among these zeros and ones, executing different instructions. If you click this menu option, it'll use this code. If you click on this menu option, it'll use this code. So in other words, the computer logically is kind of moving around among all those zeros and ones and executing them accordingly. So one of the first things your computer does when a program is running is it just jots down at the bottom of the computer's memory, what is the address to which I should return after doing this? So it's kind of like in the real world, if you go off and do something over there, eventually you want to remember to come back over here to pick up where you left off. And that's what we mean by return address. It's a little reminder to yourself that no matter what you go off and do right now, you got to come back and resume where you left off. And what this return address then does is it refers to some specific location in the machine code, some specific pattern of zeros and ones that eventually the software should come back to pick up when the user leaves off. So for instance, if you open the file menu and go to print, and you go through the steps of printing a document, the return address might be to go back to whatever you were doing in that document before you initiated the print command. So the software is constantly jumping around in this sense. So besides the return address, that return address metaphorically might mean go to the machine code, like go back to this particular location in memory. All right, but what happens though if an adversary is somehow able to provide the program with more input than it was expecting? So maybe the program asks the user to type in their name, and they type in a crazy long name with way more characters than any human would actually have in their name. Well, if the software is naive and it just loads all of those characters into memory, what might happen? Well, the user might type in, I got the story wrong, darn it. Let me rewind and say that again. So conceptually, at the bottom of this memory might be a command like go to machine code, to remember that it needs to go back to a specific location in the machine code when it's done doing some other thing. So let's imagine what this software might be doing. Suppose the software's purpose in life is to let me search for things, and I might want to search for cats. Well, if I go ahead and search for cats, that is the next thing that the software is doing, so it goes above this location in memory, its own frame on the stack, so to speak. But what if I'm not just searching for cats, which is fairly short? What if I type in something much, much longer, a longer search query than the programmer anticipated? The result might be, because this data is stored from top to bottom, as I claimed, we might have not just cats, but something else. Sorry, I messed up again. OK, sorry, let's start that one more time. Suppose now that the user just clicks some button within the software to search for something. Maybe it's like cats. Well, because this is a new function that's being called, the search function, what the computer might do inside of its memory is this. It might put a little note to self to say, go back to this location in the machine code once the user is done searching, just like the user might be done printing. And then suppose the user types in cats. Well, cats is stored in the computer's memory just above this frame on the stack, because again, I said, by convention, whenever the software uses memory, it starts at the bottom, then goes up, then goes up, then goes up. So after now the software is done searching itself for cats, then that frame on the stack is sort of removed, because we don't need to know about cats anymore. We're done searching for them. So the last thing in memory is this reminder, go to machine code. And this is how the software knows to go back to a particular location in code, where maybe it's just sitting there waiting for me to click some other menu option instead. But what if an adversary is the one at the keyboard, so to speak, and it's not a good user just typing in short phrases like cats, but maybe it's an adversary who's typing something more. So suppose that an adversary actually pulls up the search feature, and in general, therefore, the software is going to remember to put the return address there. So specifically something like go to this location in the machine code. But suppose that the adversary doesn't type in cats, doesn't type in dogs, but types in, for the sake of discussion, some pattern of zeros and ones that represents actual code. Maybe it's the pattern of zeros and ones that represents delete everything from a server, or start sending emails, or the like. Or maybe, more cleverly, maybe it means skip whatever menu keeps prompting me to register or activate my software. In other words, the adversary wants to trick this software into running zeros and ones that didn't come with the software. Now, in practice, you can't just type zeros and ones at the keyboard. It would be a different way that the adversary inputs this data. But for the sake of discussion, assume that the adversary is not typing in cats, but is typing in these zeros and ones. And they know enough about binary, zeros and ones, that they know what patterns to choose. Now, suppose that this code, this so-called attack code, is way longer than CATS, and it's many more characters or bytes long. It is possible, by definition of how memory is used, that this attack code might be so big that it takes up not only this space that's been allocated for it, but it overflows other things in memory. You can now think of this frame, this rectangular region on the stack to which I keep referring, is like a buffer, a room for some amount of information. But if the adversary provides so much information, so much attack code, zeros and ones, that it overflows that buffer, it might actually overwrite that note to self with ... something else. And what's clever here, though, is that if the adversary is smart enough, and this is often through lots and lots of trial and error, they don't often just get it the first time. If the adversary is ultimately clever enough, they can actually put not just some random zeros and ones there, but they can put the equivalent of a note to self that says, go to attack code. In other words, instead of typing in cats, they type in two things that are pretty long. One are the zeros and ones that represent some form of attack, like circumvent the registration or the activation for the software so I can use it for free, or do something else that's malicious. And if the second thing they provide in just so happens to be cleverly the address of their own attack code, which they can figure out mathematically, perhaps through trial and error, the adversary can trick the computer into not going back up here and running the machine code that came with the software. The adversary can trick the software into executing code that the adversary themselves injected. Now, what does that mean? If you are running this software under your username, whatever you can do on the software and the system, be it your Mac or PC or phone, so now can the adversary. And maybe they'll now delete all of your files. Maybe they will now all register this software. Maybe they will now start sending spam. Anything at all is possible based on what the adversary has passed in here. So if you've ever heard of a website called stackoverflow.com, which is a popular website for programmers to ask questions and get answers of a community, that specifically is the allusion to exactly this kind of bug or mistake, whereby, if not programmed properly, the stack can overflow. And if the software or programmer does not anticipate or detect it, bad things can happen. You can have arbitrary code executed, or you can have remote code executed if the adversary isn't even at that keyboard, but is somehow sending this code into your software via some network connection. So what then might this mean? So if you've ever heard of the term cracking, which typically refers to figuring out someone's password, or in this case, breaking into software, cracking might refer to eliminating the need for a serial number or an activation code or the like, because if you can inject any software, any code that you want into someone's software, you could tell that software to just skip the lines of code, the zeros and ones that represent asking you for that activation code, or they can do something much more malicious. So this is an example in some sense of what we might also call reverse engineering. Reverse engineering refers to the ability for someone to figure out how something was engineered, how it was built. Now, at the end of the day, most of the software that you and I install on our Macs or PCs or phones is pretty much just zeros and ones. So it's very non-obvious to an adversary even what is actually going on. But with certain techniques, with certain trial and error, they can actually figure out what those zeros and ones represent. And depending on the language that was used to generate that software, they might be able to glean even more information than that. Now, there's a good side of reverse engineering, whereby if you and I are in the business of figuring out how malware was implemented so that you and I can contribute solutions to antivirus software and the like, well, malware analysis uses these same kinds of techniques, trying to figure out what's going on underneath the hood of software as by reverse engineering it. So using trial and error, maybe injecting some code of our own to figure out exactly what instructions are embedded among all of those zeros and ones. Now, how might you hedge against these kinds of threats of remote code execution, arbitrary code execution with software of your own? Well, you could start using open source software, for instance. Open source software just means that the code that implements that software, be it in Python or PHP or Java or C# or C++ or any number of other languages, is itself open source. That is, you and I and anyone on the internet typically can read the source code and see exactly what instructions will be executed on your computer or phone. Now, that doesn't necessarily mean that the version of the software that you are running is exactly the same as the open source version. There's still a threat whereby the code might be open source, but maybe you were tricked via some phishing email or some malicious website into installing a fake version of some software that actually has malicious code in it. So malware might still be a problem. But a lot of folks think that open source tends to be a good thing because you can audit. Smart people on the internet can audit the code and make sure that there are no backdoors or malicious instructions that might do things that you wouldn't expect the software to do. Now, again, that's not necessarily the case that the version you're running doesn't still have some form of infection, but this might give you at least a bit more reassurance. Now, the flip side, though, is that if code is open source, even if it's devoid of anything malicious, it might still have bugs, mistakes that human programmers accidentally made, which might very well make open source software or any software vulnerable to attack. I mean, you're literally giving the adversaries the plans to your software. It's like the plans to the Death Star in Star Wars, such that they can probably figure out what the weaknesses are in your software because you're giving them the blueprint therefore. So an alternative to open source software is perhaps the default, which is closed source software. So any software that you might download or buy from companies that it's not open source is typically closed source, which means only their employees have access to it. Now, the downside is that you, the user, do not have access to closed source software. Only the authors, therefore, do. But the upside, arguably, is that now so do adversaries on the internet not have access to it. So maybe the probability that that software not only has mistakes, but those mistakes are exploited is perhaps lower. And so this is perhaps more of a debate, and you yourselves, as you consider this, might require your own opinions on open source versus closed source. But another argument in favor of open source is often that with so many people around the world having eyes on software, perhaps that actually increases the probability that we will detect bugs or detect potential exploits because so many more smart people are looking at it and therefore weighing in. The downside, of course, if one of those smart people is an adversary, they find it and don't tell anyone, then we're back to a problem from a previous class wherein we discussed those zero-day attacks. But this is one way, one mental model you might have for evaluating just how secure your own software might be that you're either using as a user or developing as a company. What's another way that you might gain some assurance that the software you're installing and using is not infected with some form of vulnerability or malicious intent? Well, you could download all of the software that you use only from an approved app store, be it in the world of iPhones or Android devices, Mac OS, Windows, or the like, whereby you have some other entity, like a Google, an Apple, or a Microsoft, a big company, that is at least analyzing the applications that are being uploaded to these app stores before they're allowed to be distributed to people like you and me. Now, that's not to say that Apple and Microsoft and Google's or others are perfect. There have absolutely been many cases where even applications in these app stores has some malicious feature that they only realize after the fact. But again, it's probably increasing the probability that some smart people or automated software is going to detect those things first before it even reaches your device. And therefore, it makes it harder for the adversary, raises the bar, raises the cost, raises the risk to them to even get something like that distributed. So what does this mean? Well, when you install software on your computer, perhaps you should get it only from Microsoft or Google or Apple and not from some random website, and certainly not from some random email that someone sent you with a link to download some piece of software. Now, that's not always going to be the case, and particularly if you yourself are an aspiring programmer, a software developer, you might need to be in the habit of installing sort of unauthorized software for which you might have to jump through some hoops and change some settings in your phone or your Mac or PC to even allow you to install unauthorized software if you know what you're doing. But these kinds of mechanisms, even though they create dissatisfaction with this idea of a walled garden, whereby you need some corporate entity's permission just to distribute your software, they do serve a good purpose as well. So there, too, you might fall on one side or the other of that sort of argument, too. Now, how do those app stores enforce the fact that you can only install the software if it is in the App Store itself? Well, it turns out we can revisit some of our primitives from past classes whereby we talked about encryption and also hashing and also digital signatures. The latter of two are particularly germane here. It turns out that cryptography really is the solution to a lot of the world's current problems when it comes to cybersecurity if we use these primitives, hashing, encryption, and digital signing, as building blocks to solutions. So for instance, when you develop a piece of software, or some company does this for you, and they upload their software to Apple or Google or Microsoft for distribution, what are those companies doing? Well, first, you as the author of the software are first using your own public and private key, which you came up with in advance, and you are running your software through some special function or algorithm and getting back a hash thereof. Again, a hash is this fixed length representation of your software. So even if you wrote a really big program, you have this unique identifier, or highly probably unique identifier, called a hash. And what you can then do with that hash is use your private key and sign that hash, giving you a digital signature. That signature can be verified by Google or Microsoft or Apple as being, OK, I know that David Malan wrote this software because I know that only he has that private key. And so long as I, David Malan, registered my public key with Apple or Google or Microsoft in advance, they can assume that, OK, this new version of the software or this new program came from David Malan and not from some random person on the internet pretending to be David Malan. Conversely, what Google and Microsoft and Apple and others can do is the same thing. Once you have uploaded your software to their app store, they can ensure that they run the software through the same function, getting back a hash thereof, a unique representation thereof. They can use their own private key from their own app store to take that hash as input and produce a digital signature, this time signed by Apple or Microsoft or Google, or whoever else is running the app store. And then when you or I install that software on our Mac and our PC or on our phones and devices can ensure that any software you and I are installing on our device was digitally signed by that app store, by Google or Microsoft or Apple or the like. So again, just by using this basic building block of digital signatures and hashing in this case, you can both attest in one direction that I am David Malan, trust my software is written from me. Conversely, when people install my software, they can trust, if Apple or Google or Microsoft or others trust that software, that they should indeed be allowed to double click it. And it's only when you download some unauthorized software from the internet, typically, that you get often nowadays on your screen an alert saying this has not been signed, or this is from an unauthorized third-party developer or the like, if they're not playing nicely in this same ecosystem. But again, digital signatures take us a long way there. So another mechanism you can consider, which is similar in spirit, but typically terminology that's used in the world of Linux computers or similar, are package managers. And different programming languages also come with an ecosystem of libraries, third-party code that people write and they make freely available, often as open source. But there's standard ways via which these package managers can let you and me install the software on our own Macs, PCs, phones, or the like. And it's using tools like pip for Python, gem for Ruby, npm for Node.js, and there's others as well, apt for Linux. These package managers, though, typically adopt a very similar mechanism whereby they are digitally signing these packages so that you and I can have our computers verify those signatures before they're actually allowed to be installed. And in general, this involves operating systems as well. The operating systems that you and I are running nowadays, at least if you stayed current and are in the habit of automatic updates or frequent manual updates, odds are today's more modern operating systems are increasingly building in native support for these kinds of checks. Downside is it's getting a little more difficult, a little more annoying to install third-party software on our devices. But the upside is that if you trust these app stores, these package managers, then by transitivity, you can, with higher probability, trust the software being distributed there too. Now this too, though, is not fail-safe. And it has often happened that even once software has been uploaded to these app stores or package managers and made available to folks, and version 1 might be perfectly safe, version 2 might be perfectly safe, version 3 might be malicious for some reason. Maybe the developer finally decided to do what their intention was all along. Maybe the developer, and this has happened too, sold their software to someone else, and the third party now is adding ads or something malicious to it. Or someone has hacked their computer or account and gained access to their private key and not just their public key, and therefore are masquerading as them. So even now, you can't necessarily trust the software you're running on your computer. But again, that brings us back to some of our earliest lessons in the class, where what we're really trying to do is raise the bar to the adversary, increase the cost, increase the risk to them, and conversely decrease the probability to us that any one of these pieces of software might actually be malicious. Now, there are models that the world has been experimenting with over time to try to figure out how best to reduce these probabilities further. And there's this notion of bug bounties, whereby some companies will actually steer in to the reality that there are people out there with the skills not only to do malicious things with their software, but also good things as well. For instance, people who might very well want to try to find bugs in software, particularly ones that relate to security, if they know that the company in whose software they're discovering these bugs is willing to pay for it. And not in a ransom sense, not in a malicious ransom sense, but in a bounty sense, whereby there tends to be this marketplace for some companies and some products, whereby if you do discover a bug in their software and you disclose it only to the designers of the software, at least during some window of time before you tell the world about it, they will pay you. So that once they can therefore fix the bug, then pay out, because it's a net positive for everyone. Win-win. You have benefited, they have benefited, and hopefully no adversaries have found it first. And depending on the severity of these bugs, you might get paid more or less based on the same. And so the idea here of these bug bounty programs is to try to leverage the collective intelligence and technical skill of people who, frankly, without these programs, maybe would be using their skills for evil and trying to hack these systems and monetize them through ransomware. But perhaps we could channel those funds instead toward paying people to do this kind of work. So this too is something to consider, not so much as a user using software, but perhaps a company developing software. So where can you learn more, and what has the world come up with to keep track of all of these possible threats? And what we focused on today really are representative attacks using some languages and technologies that are quite omnipresent and fairly accessible, at least at the level we've explained them. But it turns out that there is a whole inventory of vulnerabilities that have been detected over the years, common vulnerabilities and exposures, or CVE, such that a lot of the kinds of attacks we've been talking about today, and more specifically bugs and flaws in specific software and versions thereof, are often assigned a unique identifier, a CVE number that system administrators, companies, and even end users can keep track of to make sure they are always current with the latest threats out there. There is also a common vulnerability scoring system, or CVSS, which is a standardized way of assigning a score to the severity of a vulnerability. Is it a big deal, or is it not so much a big deal? It might still be a vulnerability, a bug, but is it that problematic? And so there's this scale so that you can prioritize, for instance, given limited resources or time, which of the bugs you should be fixing, which of the software you should be updating, or maybe which of the software you should not be using, at least while it's vulnerable to something that's highly severe. There's an exploit prediction scoring system out there, EPSS, which refers to what do people in the real world think the probability is that this particular bug or mistake in software will be exploited is. And this then might give you a sense of just how problematic it is. Even if there's something very severe, is it more of a hypothetical threat or an actual threat? Something that IT people might indeed take into account when designing how to respond to some system. And then there's a known exploited vulnerability catalog, KEV, which refers to all of these kinds of bugs that are known to have been exploited. So suffice it to say, here we're now seeing evidence of just how big of a world, how big of a space cybersecurity is, that we have all of these lists and taxonomies for keeping track of things. Because if you're feeling a little overwhelmed with just some of the concepts, imagine just how many hundreds, thousands of actual threats and vulnerabilities there are in the actual wild. So that was quite a bit here, focusing on all of these threats to the security of our software. We've just got 1 week to go wherein we'll focus on how we can preserve not just the security of our systems, but perhaps more importantly to you individually, the privacy of your information therein. So more on that next time. I messed up the ending, didn't I? Let's fix that again. Sorry. So that was quite a few threats to the security of our software. We'll take just one final, sorry, let me get this right. OK. All right, that was quite a few threats to the security of our software. Up ahead is how we might now preserve our own privacy. More on that next time. All right, can we do like a few questions? 3 questions on anything we covered today. Thank you for bearing with us for a longer one. Let's see. Abdulrahman?
Okay. First of all, hello, everyone. Is there a way to change the signature of the program so that the computer, when you try to install the program, it says from a trusted author or something?
Can you change the signature? So the idea of these hash functions are that when you run some piece of software through the hash function, it should always produce the same value. So if someone changes the software by literally changing it and tricking you into downloading it, if the hashes do, and then they hash that version of the software, that hash should not match the original. So yes, theoretically it is possible to change the signature, but it's usually a side effect of someone having changed the software for malicious purposes. And so what the operating system and these app stores are doing are comparing those signatures for accuracy. Other questions? How about from Manal? Or Mahal, sorry.
So my question is about something that we talked about near the starting of the lecture, but what are the risks of using only service-side validation?
Oh, a really good question. I might regret this, but I want to say none, to be honest. Because at the end of the day, at least for websites and web-based applications, it tends not to be a big deal if the user screws up on their own client, so long as that mistake doesn't propagate to the server. So I'm sure we could contrive a scenario where it's problematic, but I'm pretty comfortable saying you should always have server-side validation, but client-side validation just tends to be icing on the cake. It makes the user experience better. And Mohammed.
Thank you, Mr. David, and happy birthday. My question was related to the previous one, that I can make the server-side validation, and also including the SQL and Python itself. And as well, we can make the client-side. So it is better if we combine both together. It will be hard for us, but it may be better for both of us as a developer and as a user.
I feel really bad. I only heard parts of that because your mic is very quiet and there's like a wind sound. Do you mind typing that into the chat just so that Carter can try to field? I'm sorry, it's a little hard to hear that one. And I hope folks won't mind. There's a lot of questions in the air, but we want to wrap because we're going to be back at 3 p.m. Eastern for this look at preserving privacy. So I hope you'll forgive if we wrap up now. But we'll be back at 3 p.m. Eastern time today for the class's final lecture on privacy. So we will see you soon. Thank you so much. And Andrew, let's not cut yet. Can I just re-record the end real fast?